Good afternoon, friends. Today we are going to learn about our topic, that is hydrogen molecular ion. So as you all know about the hydrogen ion, that it contains one electron and one nucleus. So we will be learning about H2 plus ions, H2 plus molecules. This is the only molecular system which has been solved by quantum mechanics. So as we know, H2 plus ion contains one electrons and two nucleus. So it is equivalent to hydrogen atoms. Okay, so let us consider, let us learn how to actually solve the equation in quantum mechanics. In hydrogen atom, what happens, the atom is been separated by two spherical coordinates where the nucleus lies in the between, and for H2 plus ions it has been separated in ellipse form where hydrogen where nucleus is lies at the periphery of the system.
So as we know what is the hydrogen molecular ion, in which the one of the electron is get shed by the two hydrogen atom. So in this case what happened, there are the two cases. First is that this electron is get interacted by one of the hydrogen atom. But in this case what happened, that if electron is interacted by one of the hydrogen atom, then energy of that hydrogen atom will get increased. So we cannot calculate this. So in this case we have to consider that these electrons is get associated with both of the electrons, both of the hydrogen atom. So for this wave function is this, in which the C1 and C2 is nothing but what the time that is spent by the electrons with respect to one hydrogen atom and the second hydrogen atom. So this energy can be calculated by using the variational method. Variational method, the formula is nothing but this. So in this case, the Hamiltonian operator is this, in which this is nothing but a kinetic energy. This term is nothing but the interaction between the HA and the electron. R1b is nothing but the interaction between HB and the electron, and this RAB is nothing but interaction between these two hydrogen atoms. So this can be solved by this way. So in this case, this will get represented by HAA, HBB and this. So basically this can be solved by using the secular determinants.
Hello everyone. This was the equation of energy which we got from the variation theorem. Okay, we can also solve this equation by a secular determinant method. Okay, but in this method we have to remember HAA is equal to HBB. Now solving individually for HAA, we have to write this equation. The Hamiltonian for this equation is minus 1 by 2 del square minus 1 by RA minus 1 by RB plus 1 by R 1 SA dr. Now solving the individual two terms. Okay, the solution for this term is written over here, and the solution for this term is written over here. Taking 1 by 2 as a constant outside the bracket, the solution for the whole term is 1, and for the solution for the whole this term is j. As we know, j is what? The Coulomb integral. Now solving for HAB. Okay, so we have to write the same way. My 1SA the whole Hamiltonian, then 1SB deta. Okay, again solving for the individual terms as mentioned above. The solution for this term is S. The whole this term is S, and for this term is K. The K over here is exchange integral. Now we can also solve this by normal determinant method, like over here HAA the whole minus E the whole square and HAB minus ES the whole square. Taking square root over here, we will get a plus minus sign over here. Now while considering the ground state, take the negative sign. Okay, this is the energy level for the ground state equation. Okay, so if we took the minus sign over here, the solution for this equation was HAA plus HAB upon 1 upon S. The same way we have to solve it by taking the excited state for the plus sign. Same solution, but the reverse answer is reverse. Now let us take the solve the whole equation by HAA and HBB. The solution for HAA was 1 by 2 J. We have to substitute the 1 by 2 J over here. And solution for HABB was minus 1 by 2 S plus K. We have to substitute this equation over here. Now this is the whole value for the K. Now that will take delta E. Delta E is what? E2 minus E1. So this whole equation will be come over here plus 1 by 2. So 1 by 2 will get cancelled, and the whole answer will be J plus K upon 1 by S. Similarly, we can also solve for the in the same manner for the delta E for the excited state. The whole solution will be same. Here also 1 by 2 and minus 1 by 2 will cancel, and this will be the final answer for delta E for both the terms.
Here E and E2 is replaced by E plus and E minus. So these are my secular equations. So we'll solve the secular determinant,
and we'll get that C1 and is equals to C2 for the ground state. For ground state, we'll consider the negative sign. Okay. So to find the C1, we will normalize the function and get the C1 value like this. And also there is psi plus value is C1, and here as C1 and C2 are equal, so I'm writing 1 as A plus 1 as B. Similarly, my psi minus will be C1 1 as A minus 1 as B. So I'll get this C1 and this C1. So my psi plus will be this and this. So this will shows the bonding, like 1sa plus 1sb will form the bonding molecular orbital, whereas this will form the anti-bonding orbital, molecular orbital. So here my two wave functions are, I mean, the linear combination of atomic orbitals like 1sa and 1sb giving me the two orthogonal molecular orbitals. Okay.
So we will be comparing the H2 ion and the H2 molecule. So as we know that we can solve the Schrodinger wave equation for the H2 ion exactly, while for the H2 molecule it cannot be solved exactly. Why? We will see. So as we can see here, H2 plus ion is a uni-electronic system, while the H2 molecule is a bi-electronic system. So as we know that because it is a uni-electronic system, the H2 plus, we can solve it exactly. But while in H2 molecule, we can see that there are various factors. So one of the factor is the electron-electron interaction. Due to this, when we solve for the Schrodinger wave equation, we can see that we get an error of more than 40% while we solve it. So we cannot solve it exactly. We use other methods to solve it, which will not cover it here. So now we'll compare the stability of H2 plus and H2. So here by MOT we can see that for the H2, both the electrons are in the bonding, while in the H2 plus, as it has only one electron is in the bonding. So we know that H2 is more stable as compared to H2 plus. By the energy equation, we can see that the overlapping integral in H2 here is S, while for the H2 plus it is S square. So as we know that the lower, as the higher this in the denominator, the lower is the energy. So the energy for the H2 is lower as compared to the H2 plus. So that is why this is more stable as compared to this. Now we will see for the overlapping. As for the overlapping, we can see that while we compare for the H2 and H2 plus, we can see that the overlapping in the H2 is higher as compared for the H2 plus. So by the overlapping, we can see that the H2 is more stable compared to H2 plus. Why? Because as there is overlapping, the nuclear interaction will be lower and there will be less repulsion as compared to the H2 plus. Thank you.